axes properties, right? You're like either
Yeah,
large or shrinking. Okay.
yeah. So, but if you already have that set, if you're adding data into a plot where you already have that set up, then you want to change the auto scale on read to none. So like if I did that right now,
Hmm.
if I'll do that right now, and what's going to happen is you're not even going to be able to see the data because it's not going to change the default axes. So
Hmm.
I've read the data in, but you can't tell, right? Because because it didn't rescale everything.
Because it was a P was under like the 200. Well, it was 1 to 200.
Yeah. So if you, and remember, anytime you have a data set here, you can double click on it. And that brings up
Oh,
the
okay.
spreadsheet of it, right? So you can see, so the X is 1 to 200. That's the pressure in
Hmm.
in 10 to the 5 pascals, right? And then this is um, the molar volume in cubic centimeters, I think, right? So
Hmm.
this is one of the things you have to be careful of when you're doing calculating, is you have to be aware of the unit. So um, let me look at, I'm gonna have to find it here. So if we look at, I have the exam key here, it's probably the easiest way to look at it. So if you look at the data, right, here's the data originally. And this is the cubic, or the molar volume is in cubic meters per mole. All right, that's fine. Just so we know what it is. But that's an SI unit. So what you want to do when you're doing any calculations is being aware of this. So for example, oh, this is 10 to the minus 3 cubic meters. So this is actually, the number is actually 0.055, right? Does that make sense?
Hmm. Because you
Right,
go,
so
okay.
that's kind of a standard thing. So when you're doing calculations, you have to take that into account. So if I want to do a manipulation here on this data to to um, to fit um, to fit the numbers, the first thing I'm going to do, right? Really, the first thing I'm going to do. Let me get my iPad going because then I can write stuff. Okay. So the first thing you're going to want to do is like a sample calculation to know what you've got, right? So
Hmm.
if I look at the data, like I have P in units of 10 to the 5 pascals, 1, that's the first one, right? And
Uh-huh.
then down here I have 200. And then I have the molar volume in units of 10 to the minus 3, 10 to the minus 3 meters cubed per mole. And I have 55.896. And I've got, the last number I've got is 0.17918. So if I was just plotting this data, then this data here from this table, then those would be my limits. But
Hmm.
the equation here is we're looking for the fugacity coefficient. So we're looking for
Yeah.
this thing, the phi. And so the equation is this, the integral of 0 to p prime Vm over RT minus 1 over p dp. Right? So this is what we want to plot. Right? So this is some function of p dp. So we want to plot that. And the idea is, right, we're going to have, this is going to be our function f of p. And hold on a second. This is going to be our function f of p. It's going to be points, right?
Hmm.
Then we're going to fit a line to this, right? So this is going to be our fit of P, is going to be some polynomial, right? And then in order to do this integral, we're going to make the substitution this. Right? In other words, we're going to just plot, we're going to do the kind of point-by-point conversion. Which is going to give us our function, you know, our points.
Mm-hmm.
We're going to, I should use different colors. We're going to do our fit to those points, right? So now we have a continuous function. If we have a continuous function, we can numerically integrate that, right?
Okay.
And so this is going to be some number. And then we're going to, you know, be able to find out what the phi is. So that's what we're going to do. So the hard part is this, is doing that. So what you want to do is you want to figure out what these values are. And the first thing you should probably do is do a sample calculation. So for example, Vm over RT minus 1 over P. Now, naively, and this is the tricky part, right? It's 55.896.
Mm-hmm.
So we're just going to do a calculation on paper here, right?
Yeah.
Times 10 to the minus 3 meters cubed per mole. Divided by RT. Well, R is 8.314
Mm-hmm.
joules per mole per Kelvin, right? That's the SI unit, right? So you want to make sure you're always using SI units, and then you don't have to worry about units canceling. They're just going to cancel. And then it's 400 C, right? Which is 673.15 Kelvin.
Mm-hmm.
All right, so what's going to happen is the kelvins are going to cancel here and the moles are going to cancel here. So we're going to have units of meters cubed per joules. But if you look at these two units, have to be the same, right? I mean, or else I can't subtract them from each other. So these units must be inverse pascals. They've got to be. Does that make sense? Because if I have units attached and I'm doing, you know, math, then the units have to match, because I can't subtract like feet from pascals. Does that make sense?
So once you cancel out the moles and Kelvin, so all you have left is meter cubed over
Joules.
what? Oh, okay.
Over joules, right? But that's got to equal inverse pascals. It has to, because it's all SI units.
Because inverse pascal represents the minus 1 over P, right?
Yeah, exactly.
Okay.
So what I'm saying is, so what I think a lot of times students do when they're messing with unit, if they're, first of all, the first thing they do is they don't concern themselves with units, which is wrong. Mm-hmm. Right? I mean, you always have to worry about the units. The second step is that, oh, I've got to make sure these units are all the same. So I've got to convert joules to whatever the SI units are and make sure everything cancels. And I have to go back. But if you always use SI units, they will be right. Does that make sense? So if you just make sure that your units are all SI units, then you can just like trust that they work out. And maybe the one time out of 1,000, somebody made a mistake somewhere and it'll screw you up. But right, so it's kind of like you just have to trust almost. Does that make sense?
Yeah.
So that's the first part, right? The 1 over P is 1, but the trouble is this is 1. If you go up here, right, this is 1 times 10 to the 5 pascals. Right? Mm-hmm. So you just have to, so in other words, this is going to be minus 10 to the minus 5th pascals minus 1. That's what that subtraction is. So now we can do all the other multiplication. And don't forget about this 10 to the minus 3. So this would be the same, you know, if you weren't even plotting this, you would have to still worry about all this junk, right? But what we're doing here is we're going to do this once, because we only want to do it once, and once we figure out how to do the calculation, we're going to tell Grace to do all the other points. 8.314 divide 673.15 divide. All right, so this part here is 9.9875 times 10 to the minus 6 inverse pascals, and I'm subtracting 10 to the minus 5 inverse pascals. So this is going to be a negative number, right?
Mm-hmm.
It's pretty, I mean, it's pretty close. They're almost the same, but that's the whole point, right? Because we know that this difference is small. That's kind of the whole point. So this turns out to be 1.300 something times 10 to the minus 8 inverse pascals when you do this, right?
You subtracted that, right?
Yeah, I subtracted them. So this is my answer. This is my answer for my first point. So in other words, I could go up here, right, and write down, I'm going to call this f of p, just because I don't want to write the whole thing in. And for this first point, it's minus 1.300 times 10 to the minus 8 inverse pascals.
Okay.
So that's my first point that I'm going to plot on my new plot, right? But I don't want to have to calculate all these points myself, right? I mean, you can, but then you have to add them in. And so here's what we want to do. What we want to do is we want to translate the calculation we just did into Grace speak, right? In other words, we want Grace to do this for us. So let me do a couple things here. What I really have here is I have my original X, right? Or I'm sorry, my original Y value, which is VM, right? For my original data up here, this is the Y. This is the X. So in Grace, I'm going to use those two generic variables to refer to my data, X and Y. Right? So what my calculation, if you look at my calculation was Y times 10 to the minus 3, right? That's because the table took that out, but we have to put it back in for the real number. What I do when I talk about doing this in answer keys or in class, what do I say? I say, you want to make, I say it makes it agreeable. In other words, if we didn't do that, then the number on the plot would be 0.00558. It just doesn't look as nice, right? We want numbers that just look like, you know, maybe between 1 and 100 or something like that, right? So then so that's why on plots lots of time you see the 10 to the minus 3 or 10 to the 6 as part of the unit, right? Because we're just moving the decimal. It's weird. I mean, it's weird, but physical chemistry. So we have to take that 10 to the minus 3 in account, just like we did up here. And then what are we going to do? Every time we're going to divide by 8.314 times the temperature. 8.314 times 673.15 times. That equals 559. 6.6, right? So that's the RT. All right. And then I'm going to subtract 1 over the X, right? But it's going to be 10 to the minus 5 on top. In other words, it's 1 over 10 to the 5, which is 10 to the minus 5 divided by the value. Does that make sense? So in other words,
Mhm.
I'm trying to set it up so I can type it into Grace in a way that both Grace and I understand
Yeah.
it. Okay. Okay. Now the other thing is when we're done with that calculation, the answer is some number times 10 to the minus 8, right?
Mhm.
So let's
Yeah.
do the physical chemist thing and multiply this by 10 to the 8 to make the number a number. I mean, let's make the number minus 1.3 instead of minus 1.3 times 10 to the minus 8. Does that make sense?
Mhm.
So when I plot it, I don't have to, I don't have to put that. I don't have to put that in every point. So here's what I'm going to do. The first thing I'm going to do is I'm going to absorb this 10 to the minus 3 into the bottom. 5, 5, 9, 6, 6, 0, 0. Right? Do you see what I did?
Uh-huh.
Instead of multiplying by 10 to the minus 3 on the top, I'm going to multiply by 10 to the 3 on the bottom.
Mhm.
Does that make sense?
And that would cancel out the 10 to the minus 3 on the top, right?
Yeah, that puts it on the bottom and just makes the number bigger on the bottom.
Mhm.
Right?
And you do the same for, would you do the same for the second term, or you just
Well,
leave it like that?
I could.
Oh, no, because it's an extra, right? So
Right.
it
But
wouldn't
the
work.
other thing I want to do is multiply the number by 10 to the 8. Right? So then what that means is when I do my plot, I'm going to say Vm over RT minus 1 over P divided by 10 to the minus 8, and then whatever the units are. I guess it's pascals minus 1. So this is what my units are going to say on my plot. When I put this in my calculation, it means I have to put a corresponding value there, right?
Mhm.
But what I'm going to do for the other thing is I'm just going to plot P in, well, I'm going to leave the P the same. I'm going to end up plotting the P in 10 to the 5th pascals. I don't want to do I don't want to do anything with that. So in other words, my X is going to stay the same. I'm just going to change my Y into a function of Y, because that's what's inside my integral, right? You remember what we're going to do is we're going to convert every single point. We're going to transform every single point, right?
Mhm.
We're going to numerically fit those points, and then we're going to integrate the fit function to find the value, right? So when I do all this, I'm going to end up that my f of p is going to be y times 1e8 over 5596600 minus, now, so that's that one, but I also have to do this one, right? So this is going to be
Mhm.
1e3. 10 to the 8th times 10 to the minus 5 is 10 to the 3, right? So this is what it's going to look like when I put it into Grace. And if I do it right, then the first number is going to be minus 1.3.
So the 10 to the minus 8. So you got that because we calculated the first point by hand.
Yeah, so let's go through it again. It's worth going through it again. So here, this is our answer for the
So
first point.
that's our first data point. At least
That's our
our
first
first
data
new
point.
yeah.
It's small. It's has a factor of 10 to the minus 8, right? So when I
Mhm.
plot it, I don't want that. I want to kind of divide that out so I can just plot minus 1.3 instead of 1.3 times 10 to the
Oh,
minus
okay,
8,
okay.
right? So the first of all, what I'm going to do is I'm going to multiply all my numbers by 10 to the 8. That's this,
Okay,
right?
I see.
So here's my function. I'm going to multiply all my numbers by 10 to the 8 just to make my result minus 1.3 instead of minus 1.3 times 10 to the 8. But what that means is when I plot this first point that's minus 1.3, here's the data point. It's not really minus 1.3. It's minus 1.3 times 10 to the minus 8. So what I'm really doing is I'm dividing by 10 to the minus 8. In other words, multiplying by 10 to the 8.
And then you made that clear in the axis title, right? By adding the 10 to negative 8.
Yeah.
Okay.
Yeah. So I'm telling people what I did, because they're going to go home and do the same thing, do the same experiment. And they're going to say, why did we get minus 1.3 times 10 to the minus 8? And then they say, oh, it says it right here.
Mm-hmm.
Right. Okay. So let's go back to Grace and see if we can figure out how to tell Grace to do this. Now, I have to say, it can be confusing. Here's my spreadsheet data. I haven't done the transformation yet. So what I'm going to do is I'm going to go to data,
Professor,
transformations.
your screen's not sharing. I can't see anything.
Why? Oh, I forgot to share it back again.
Yeah.
I forgot. Come on.
Okay.
Okay. So, all right. So I go to data, transformations, evaluate expression. So this is going to let me create a new data set based upon a formula that I type.
Okay.
So I want to click this. And again, Grace, it lets you use a generic X and Y, right? It actually refers to the X's and Y's as G0.S0.Y. And then the data points would be Y1, Y2, and so on, right? But if it allows us to treat them generically with an X and Y, which is actually really nice, right? So you don't have to remember all that, which set you're working on, whatever. So I'm just going to go back to what I wrote down and try to make this right. So the formula is going to be, my new Y is going to be my old Y, and I'm going to use liberal. You want to use parentheses liberally, right? To make sure that it's as much to make sure that you understand what you're doing as Grace does, as the computer does. So it's going to be the old Y. So in other words, it lets you kind of recursively define the Y, which is nice. 1E8. Now I have to tell you, I kept getting the wrong answers when I tested it. So this is why you test it. You do it on paper, you know what the answer is, right? And then you're going to tell Grace to do the same calculation and you check it. Because when I did this, I was typing in 10E8, right? Doesn't that make sense? 10E8 means 10 to the 8th, right? But
yeah.
It's not. 1E8 means 10 to the 8th. And so I was off by a factor of 10 every time I put one of those in there, and I couldn't figure it out. And that's why. And it's because I'm not really a programmer, right? I mean, I'm a computational chemist, but that doesn't mean I'm very good at it all the time. All right, 1E8 divided by, so then I have this factor, 5596600, which is basically RT, right? Minus 1E3 divided by X, right? So that's going to be, that hopefully will do it. I've highlighted the data set I want to manipulate and I hit apply. All right, this creates a new data set. It's still not showing up here because my axes still aren't, but I want to see what the numbers are, right? So now I'm going to double click on this. And it says the first data point is minus 1.25. Well, that's pretty close. It's close enough that you've probably not made a mistake. Now, one thing that's really interesting, because I mean, you have the answers to these things, right? I mean, the answers are available to you. If you look, let me see if I can. So actually, I don't, in a problem like this, I have to tell you, I don't really care if you don't get the exact answer. And I'll show you why I don't really care if you get the exact answer, because I have to find the file. I organize things consistently, but that means I can't find. Okay, here we go. So if you look at the solutions here, this is a problem in DeVoe. Here's the problem. Here's the you can see this table.
Mm-hmm.
Okay, so here's the result. Here's that one VM over RT minus 1 over P, and you see 10 to the minus 8, right? To make his first result is minus 1.302. When I did it on paper the first time, I got minus 1.309. Now, when we're doing it in Grace, we're getting minus 1.2508. You know why that is? It's because I used 8.314 for the R once. I used 8.3145 one time. I used 673 one time, 600. So if you're off just by this teeny tiniest in what you represent for your R or your T or whatever, it changes the numbers seemingly a lot, right? So this to me, I like if I was looking at, let's say you went through and did this problem exactly the way we're talking about right now, and you wrote down your numbers or your data points or whatever, I wouldn't expect to see these exact numbers.
Mm-hmm.
In fact, if I see these exact numbers, I think you just copied it from the solutions, right? Mm-hmm. Because in my experience, I am unable to get those exact numbers. I have, if I use, and he doesn't give enough detail exactly what he did in his calculation, right? And here he says 1.300, and here he says 1.302, which is it. But, oh, that's the extrapolation. This is the extrapolation. I think here I got 1.309. Anyway, it's always going to be a little bit different. But that's why we always have uncertainty, right? Mm-hmm. So that's good. I mean, I want to see that. And anyway, so these numbers look like they should. They're in the ballpark, right? I mean, they're like less than 5% difference when you do these. So now we're ready to plot. We're ready to plot this, but to show them, we need to fix the axes, right? Mm-hmm. So let's go over the axes. The x is going to run from 0 to 200, right? And what you want to do so Grace doesn't complain is you want to think ahead and change the major spacing.
Yeah.
So it doesn't give you that error. So you hit apply. And it does say too many ticks, but that's because of the Y. So now we start to see our data. But this is the original data. This is the molar volume data that we're not really interested in. So let's go to the Y-axis, and it's going to run from about -1 to -2. -1, -2. And those tick marks are still okay. All right, so there's our data. Now, I have to tell you, something does look funny about that first point. I'm not quite sure why.
Because of the sharp, it's weird because of the sharp dip, right?
Yeah, and when I did my solution, I didn't get that, but that's okay. That's, like I said, that's okay. That's not really the point. We might expect that. Mm-hmm. Now, what you can also do in here is you go ahead and put the label in, right? This is good practice. We're going to plot that function, which is parentheses. Now I need an italic. Technically, I need an italic font. 5/5 is italic. V. Now I'm going to have a subscript /S, but the M in VM is not an italic M, it's an upright M, right? Because it stands for an actual word, not a variable.
Mm-hmm.
That's the rule. So now I need to go back to a regular font. So to reset the font, I do /F curly braces. There's the M, and I can test this, see what it looks like. So that's what it looks like.
Okay.
But this is over RT, and it's italic again, right? So 5 RT, apply. But I forgot to go back to upright. Superscript is small/small s. I'm sorry, superscript is /big S. Subscript is /small s. Normal is /n. Now, so that resets the baseline. And I think you can do fractions, but that's pretty hairy even for me. All right, so now I want a minus sign. I need to go away from the italic font again because I don't want my numbers to be italic. 1 over, but now I need italic again. 5p. Now I need normal again because my, so if you think about it, writing mathematical expressions pretty, like typesetting them is pretty complicated.
Mm-hmm.
All right, so that's the expression, right? But we have to put the units in now. We're dividing by 10 superscript -8 normal pascals superscript -1. And it's slanty. So I forgot to reset the font. Where am I at? I have to do it after the P. This is really tedious, I know. All right. So that's the label axis for the Y. The X is much easier, right? The X is just P/10 to the superscript 5 and actually 5. I mean, it's complicated. It's a pain in the ass. Oh, that's right. It's not -1. Okay. So there's my labels, right?
Mm.
Now, don't forget to save it. What happens to me? It hasn't happened for a while. It's unpredictable. Hold on, I clearly cannot do more than one thing at a time here. Classes. Okay, so what was I going to say? This Qt Grace crashes sometimes, and I can go days and days and days without it crashing, and it'll crash like every time I use it. Sometimes I think that has more to do with my system than the program, but you should save the file like when you do one little thing, because all writing the fonts and everything out is a pain in the ass, right? So you don't want to have to do that over again. That would really suck. All right, so now let's go to our set and let's get rid of the line, right? Because we want to use, we don't ever really want to put a line through our data to begin with. So there's my symbols. I always like to fill them. That's just what I like to do. All right, so there's my data, right? Okay, so now save again. Now we're going to do a regression line through this, because now we've gotten to the point we've plotted the data. This is just the function inside the integral. We want to get the integral, and the easiest way to do that is get a numeric approximation to this curve, right? And then we'll integrate that piecewise. So now what we're going to do is we're going to go to data, transformations, regression. This is a little confusing to me because it says transformations and you say, oh, I want to fit it to a polynomial. That's not linear, right? So you look and you say, oh, nonlinear curve fitting. But when you use nonlinear curve fitting, you have to define the function yourself, which is a little bit of a pain. If you use the regression, it has this pull down, which you can choose what you want to do, polynomials. So I always just try a cubic. If it's not a straight line, I just always try a cubic, right? We're going to load the function because we want it to tell us what the function is. So we're going to load the functions. We're going to start at 0 and we're going to go to 200. Sometimes if you let me mention one other thing here. Let's say that our data didn't start at 0. Let's say our data started like 25 or something, but we want to find the intercept where it hits 0. We might want to make the function go further. So let me change the limit here to -10, right? So now here's 0, and let me change this to 250. So now my data is more within the plot. When we do data transformations, regression. When we do this start and stop, if we want the line, we don't want the line, we want the line past the points, right? So we want the line to fill the plot, not just where our points are. So that's what you do here. I would say, oh, let's take this to -10 and make this go to 300. That will definitely go past my points. And then you say number of points. If it's linear, then you only need 2 points. But if it's a function, I don't know, I just usually say like 200. And that makes the line look like a nice curve. And then you say accept. And you see what it does. Well, that looks pretty good. That looks like a pretty good fit. And here's your equation, right? So this is your function. So this is that function that's going to go inside the integral that you integrate now to get a numeric value, right? But you have to, and I'm gonna write this down on my iPad before we go back to the iPad. Minus, I still think that first value, I think I must have done something wrong somewhere because that number looked a little bit off, but 00301, 0030169 x minus 1.1589 times 10 to the -5x squared minus 4.9325 times 10 to the -8x cubed. All right, so that's my function. Right, so you wanna write that down and save it, because now we're really done with this. Like if you're going to turn this in for an assignment, then what you would do, right, is you would go to File, Oh, you could just, in this version of Grace, you can just directly export it to a PNG, right? So now you have a picture. But you're done with this. So what we're going to do now is we're going to go back to our paper, right? And here I wrote down the function.
Mm.
But to make this easier, we're going to call this A plus B x plus C x squared plus D x cubed, right? Because we want to do the integration.
Mm.
What we also have to realize is that each of these are multiplied by 10 to the minus 8. Remember that 10 to the minus 8 factor?
Mm.
We have to reapply that because Grace just had the numbers without that factor in them. So when we did the regression, it's missing that factor. We have to put that back in. So A is actually minus 1.2669 times 10 to the minus 8. B is minus 1.1589 times 10 to the minus 13, right? Because it's 10 to the minus 5. Oh, wait, that's wrong.
Yeah, that's
1, 2, 3. It's actually 10 to the minus 11. C is minus 1. Oh, and it's,
yeah, the 0.003.
yeah, that's wrong. It's 3.01. So I moved the decimal place.
Oh wait,
right?
Is A the 1.2669 and B is the 0.003?
Yeah. And this is like, if you were doing this as an assignment, that's what you would want to be clear about. 669 times 10 to the minus 8. B is minus 3.0169 times 10 to the minus 11. C is minus 1.1589 times 10 to the minus 13. And D is minus 4.9325 times 10 to the minus 16. So those are the real values. But what we're going to say is the thing that we're trying to solve is this. A plus B, and it's P, right? It's not X. BP plus CP squared plus DP cubed DP. So this is going to be, now we have to talk about the limits, because it turns out that this fugacity coefficient is not just one value, right? In order to get the fugacity coefficient for, say, 100 bar, you have to integrate from 0 to 100. If we want it for 200 bar, then we have to integrate from 0 to 200, right? So this is really a function of pressure itself. So you can't just get one value. It turns out the fugacity is pressure dependent. And if you look at the text, if you look at the text that plots the fugacity, you can see that it changes. This is another subtle subtle point that can be hard to get. So if we let me do it this way. Log of phi at P equals 200 bar is going to equal 0 to 200 A plus BP plus CP squared plus DP cubed DP. In other words, it's going to be A times 200 minus 0 plus B times 200 squared minus 0 squared plus, over 2, right? Because this is going to be A
The integral of
P plus B over 2 P squared plus C over 3 P cubed plus D over 4 P to the fourth, right?
Mhm.
Okay, so that's the integration. C over 3 200 cubed minus 0 plus D over 4 200 to the fourth minus 0. And it looks like it's going to be a big number, but these are all negative, right? Because they're just all negative.
Mhm.
But of course, as you multiply by the square or the cube of the pressure, the prefactor gets smaller and smaller anyway. So this turns out to be, I forget what it turns out to be. It turns out to be less than 1. Is it 0.3? It's about minus 0.3. So that means the phi is about 0.7 something. So the way you do this is you say the fugacity at 200 bar equals that phi at 200 bar times 200 bar.
Okay, that's what you got. Okay.
And this is about 150.
Wait, so how'd you get from the negative 0.3 to 0.7 again?
Because this was the logarithm of that.
Oh, okay.
So then you take e to the minus 0.3 to get, and then the concept check of this, right, which is what a guy like me is always worried about, is what does it mean? The fugacity is what the pressure would be if the gas was an ideal gas to give the same effect, right? In other words, this system, we do this experiment and the pressure gauge on the experiment says 200 bar. So this gas is at 200 bar, right?
Mm-hmm.
What, and that gives a certain result. Whatever it just, and we're not even really doing the result, right? We're just basically, we're basically, how can I phrase this? The real pressure is 200 bar, but an ideal gas we'd need a pressure of 150 bar for the same effect, right? In other words, this gas, the non-ideal effects make the pressure a third more than an ideal gas.
Okay. I see.
But if we want to use the ideal gas law, on the other hand, another way to say this is if we want to use an ideal gas law to describe this gas at 200 bar, we would have to make the pressure in the ideal gas law 150. And then the other things would work out the way we would expect.
Mm-hmm.
That's what fugacity is supposed to do. Fugacity is supposed to be the real, the real pressure. Or I don't, it's hard to phrase it to get it across properly, but it's this weird concept that you have to use a reference pressure, right? Because that's the only thing that we can really calculate exactly. And that's why we have all these different equations of state, like the van der Waals equation or a virial expression, to try to account for that separately. Mm-hmm. But that's the chemistry, right? We also did all this grace stuff to try to figure out how to do grace. So that other, you know, the other plot is much more straightforward, right?
Yeah.
Because all you have to do there is do like a linear regression, and just read the data in directly. But like I said, I'm afraid nobody really did this problem the way I envisioned. So, I don't know. You're not really behind the 8 ball too much on this problem, I don't think.
Yeah.
At least compared to your classmates.
I guess like all of us haven't used Grace before, so yeah, we don't know like what to do on Grace, like in terms of like using all
Yeah.
the different tools.
Yeah, and I don't know unless people ask. I don't know. I have I have the videos up and so on, but I don't know. Um, it's just hard for me to tell what's clicking and what's not.
Yeah, this makes sense to me. The whole using the getting from one data point to another. That makes sense now. Good. That's what I was really confused about going from
Yeah, you
my
could.
first
I
year.
mean, you could, and again, assuming you knew, assuming conceptually you knew what you had to do, right? That we kind of mapped out in writing before we went back to Grace. You have your original data set. You have to realize that you need to use that data to put it in the functional form that allows you to find the coefficient. And so then you have to plot that, right? And so once you have to convert it to VM over RT minus 1 over P. Once you know that, you could do that on paper, right? You could do that one sample calculation we did, you could do that 12 times and just then enter that into Grace using the spreadsheet
Yeah.
or a data file, right? You could do that too. Um, but what if you had 120 points? Well, then it might be worth it to figure out how to talk to Grace, so
Mhm.
if only so you don't make mistakes, right? So that's a big benefit to having the computer do it for you, because once you have the calculation down, if you repeat the calculation, there's probably a pretty good chance, there's probably like a 50% chance that you make a mistake, right? So, when I was your age, when I was your age and we did this kind of stuff, a lot of these calculations by hand, um, on a calculator even, really, but we just wrote them down, right? Because our plotting software wasn't to the point where it would do this kind of stuff for us automatically, or through a function. We'd hand it over to the next guy, your lab mate, and say, you need to check these data points for me. And he's like, how many? Well, I have 100 I have 100 data points. Oh, that's going to take me all day. I'm sorry. I'll do it for you next time. You know what I mean? Because that's what you had to do. You had to check it
Yeah.
carefully by hand. And then if you had this data point, like this one here that I feel funny about, you'd say, well, I don't know why, but there's that first data point doesn't look right to me. So pay extra attention to that. And I really don't know why that one is off, unless, what I bet I did? Oh no, I couldn't have, because I read the data. I don't know what's wrong with that data point. It's definitely off. But anyway, it's at some point, if you're doing science, you're going to have to do plots or present your data, and all plotting software does what Grace does. It might do it a little differently here or there, but it's kind of like, once you kind of understand how these things work, and you might find that, I know there's a program called Origin, right, that for PCs, but it costs like $1,000, right? And so if and if you want to pay for it, you can pay for it, then you can do it. But it does similar things to this too. There'll be something in there where you can enter the function, and the syntax will be really similar. And the only difference is the interface, right? Where everything is in the menus is different. So it's like once you kind of know how to work with a program, it's just a matter of figuring out what the new program, what its layout is. It's kind of like once you work with a word processor, you can do a different word processor. You might not know where anything is, but it's there. It's there somewhere.
Yeah.
So yeah, I'm planning, on each of the following tests to have a plotting program, or have a plotting problem,
Okay.
because to me that's always, in a regular semester when we have tests that you can sit down and take, well, that's great because we can sit down and you can take them in an hour or whatever, and but you can't really solve a real problem. You just don't have enough time.
Yeah.
So if I can give you 12 hours or 24 hours or whatever to do a problem that you have to do a plot for, then you can finish the problem and say, oh, I actually measured something that means something. I don't have to fill up the test with a bunch of derivations or kind of just plug and like plug and chug problems. It's a lot more sophisticated than a freshman year plug and chug problem, right? But it's still the same. These like mini projects, I think, are a little bit more satisfying.
Yeah.
So
Okay,
what I would
thank you for that.
suggest now is go back and do problem 1 again.
Okay.
I didn't look at your problem 1 yet, so maybe your problem 1 is perfectly fine. But go back and do that, or just do another simple manipulation. Try to figure out how to manipulate data. What if you just plotted, if you plot like P versus V, right? It looks like this. It's like an exponential curve. And what law is it? It's one of the basic laws is that PV is a constant, right? So if you plot P versus 1 over V, or V versus 1 over P, it should be a straight line. So you have this data already, right, from this problem. So just try a simple manipulation, convert it from V and P to 1 over V and P in Grace, and see if you can get that straight line.
Okay.
Just as a practice.
Okay.
Yeah.
I'll go ahead and get working on that.
Yeah, try that, and don't be shy about asking for help for this. This is, I think, because every time I teach this course, I learn a little bit more about teaching it. So I think next time I teach it, especially with this book, because I think this book is kind of designed that way, and I just didn't fully understand it first. I think like we could spend like the first week just doing math, which I'm sure will make lots more people want to take the course. but I mean, for the people in the course, if we spent just a week like doing math, maybe it would help. But on the other hand, sometimes it's hard to connect what you're doing mathematically to why it's pertinent in chemistry. So I don't know.
Okay.
But hopefully that was helpful.
Yeah, thank you for the help. That was very helpful.
Yeah.